Hi everyone, this is Dr. K. Kannan, Assistant Professor, Department of ECG, R.M.K. College of Engineering and Technology. So in this video lecture, I am going to discuss about the propagation of light in optical fiber by mode theory. So this is a topic which is going to have in our Unit 1, Introduction of Optical Fibers. So first of all, we should know about what is the propagation of light in optical fiber. So the propagation of light in optical fiber, we have two different techniques. One is ray theory approach and another one mode theory approach. So in ray theory approach, to get a clear idea about the light propagation inside the optical fiber, so that is called ray theory. And for mode theory, to understand the behavior of light inside the optical fiber cable. So inside the optical fiber cable contains the properties of absorption, attenuation and dispersion. So here the mode is electromagnetic wave travels in a waveguide of different speed. So ray theory and mode theory approach is to find out the propagation of light in optical waveguide. Then the optical fiber modes. So the propagation of light along the fiber waveguide can be described in terms of set, set of electromagnetic waves called modes of the waveguide. So the set of guided electromagnetic wave inside the fiber is called modes of the waveguide. So in this set of guided electromagnetic waves, only a certain discrete number of modes are capable of propagating along the guide. So these modes are those electromagnetic waves that satisfies the homogeneous wave equation in the fiber at the boundary condition at the waveguide surfaces. So then we can talk about the plane waves. So the plane wave, it is a light wave, can be represented in terms of the wave is called a plane wave. So plane wave surfaces are parallel plate normal to the direction of propagation. So normal to the direction of propagation means it is a perpendicular in nature. So in plane wave, we are going to talk about three different characteristics. One is direction of the wave propagation and amplitude of the wave, and next one wavelength of the wave that is propagated in a particular direction. So then next one we are going to discuss about transverse magnetic and transverse electric waves, that is called a TM and a TE wave. So in this diagram you can see that which one is electric field and which one is a magnetic field when the wave is propagated in a particular direction. So light inside the optical fiber can be defined by the electromagnetic wave. So the electromagnetic wave is composed of an electric field and a magnetic field. So the combination of electric and magnetic field is called electromagnetic wave. So if the magnetic field is in the direction of the propagation, then we can call that is transverse magnetic mode. So if the magnetic field is in the direction of propagation, so if the electric field is in the direction of propagation, then we can call that is transverse electric. So transverse magnetic and transverse electric waves. The next one, what is transverse electric mode? So the electric field is perpendicular to the direction of propagation. For example, if the wave is propagated in the either direction, then the electric field in that particular direction is equal to zero. That means E is at equal to zero. But a corresponding component of the magnetic field is perpendicular to the propagation. Then the mode is called a transverse electric mode. Then next one, transverse magnetic mode. So here the component of electric field is in the direction of propagation, but the magnetic field corresponding to the direction is equal to zero. So H is equal to zero. Then we can say that this is called a transverse magnetic mode. The next one, modes with mode number we can represent by the suffix TE suffix M and TM suffix M. So all are in small letter that represents the number of modes can support. Then the combination of TE and TM is called a transverse electromagnetic mode. So the field lies in the transverse plane, both EZ and HZ are zero. Then we can say that wave is called a transverse electromagnetic wave. Okay, then the propagation of light in an optical fiber. So the propagation of light in an optical fiber is described by using electromagnetic theory concept. So in electromagnetic theory, we can obtain the detailed understanding of the propagation of light in an optical fiber. So what is the necessary to find out the field behavior or to understand the propagation of light in optical fiber? We should know about the Maxwell's equation. So now what is the necessity to solve the Maxwell's equation here is where we can go for the Maxwell's equation, then very complex analysis we can take that can be represented in terms of qualitative aspects only. But the light has a variety of electromagnetic wave vibrations, so that electric and magnetic fields are right angle to each other and perpendicular to the direction of propagation. Then, then we are going to define what is a race and what is mode. So for monochromatic light fields of radiant frequency omega, then a mode traveling in the positive z direction can be represented by exponential of j of omega t minus beta z. So omega it is angular frequency, and the time it is with respect to time variation in a particular direction, and b it is a propagation constant, z it is in the direction. So the factor b is in the z component of the wave propagation is given by a constant k equal to 2 pi by lambda. So a guided mode traveling in the z direction can be decomposed into a family of superimposed plane waves that collectively form a standing wave pattern in the direction transverse to the fiber axis. Then the mode theory for circular waveguide. So under this heading, we are going to talk about the power propagation in a fiber is used and it is necessary to solve the Maxwell's equation subjected to the cylindrical boundary condition. So to understand the optical power propagation in the fiber, we needed to know about the solution of Maxwell's equation under the condition of cylindrical boundary condition. Then it shows the outline of such analysis will be studied here based on the equations. Okay, so what is the overview? So overview of the Maxwell's equation. So when solving the Maxwell's equation for a hollow metallic waveguide, only transverse electric and transverse magnetic modes are found. But in optical fiber, the core cladic boundary condition leads to the coupling between electric and magnetic field components. So the combination of electric and magnetic field components inside the core and cladding boundary. So these modes are called hybrid modes. So hybrid modes are EH. So EH means if it is EH means then electric field intensity is larger, and HE means the magnetic field intensity is larger. That is H is larger. Okay, then the next one, the difference between refractive index of the core and the cladding. If it is very less, so very less than 1, then we can describe the guided and the radiation modes is simplified form from the component of 6 component of electromagnetic field to 4 field components. So these modes are called planar dielectric slab waveguide. So in this condition, the modes are called planar dielectric slab waveguide. So look at the diagram where we can have three things. One is the center part, it is the core of refractive index N1, and above and below we have the cladding refractive index N2. And first one we have TE0 and TE1 and TE2. So in cladding, the ray which is propagated inside the cladding is called exponential decay, and in the core where we have the wave variation in the form of harmonic, and the below which again we have exponential decay. So at the center we have the harmonic variation, and at the both the cladding, right, above the core and below the core we have cladding where the field rays are decaying exponentially. So the order of the mode is equal to number of field zero across the guide. So look at the diagram from the cladding to core and core to cladding. How many times the fields are crossing zero? That is called order of the mode. So field vary harmonically in a guiding region, and it is decaying exponentially outside the region. That means in the cladding. For lower order modes, fields are concentrated towards the center of the slab. Then we are going to talk about what is mode. So we know that the ray path in a given fiber, right, inside the core, what is the ray path? That is called mode in general. So based on the condition of the propagation constant, we have three modes. One is a guided mode, and another one radiated mode or cladding mode, and another last one it is a leaky modes. So guided modes means modes traveling inside the fiber along its axis. So they are finite solution of Maxwell's equation. So these modes contain the finite solution of Maxwell's equation. Then we go for radiated mode. So modes that are not trapped in core. So these result from optical power that is outside the fiber acceptance being refracted out of the core. So some radiation gets trapped in cladding, and that causing cladding modes to appear. So in radiated mode, the coupling between cladding and the core it is possible, and the cladding modes are supposed by lossy coating. So this is called a radiated mode. Then third one it is called a leaky mode. So where the partially confined to the core region and attenuated by radiating the air power. So this radiation results from quantum mechanical phenomena of tunnel effect. So modes we have three different types. One is guided mode, second one radiated mode, and the third one leaky modes. Then we are going to represent the TE, TM, TEM mode. So look at the diagram, the variation. So the blue color represents the electric field and the red color represents the magnetic field variation. So the modes, with the mode number, we can represent the denominator, so suffix value TEM and TM mode. So the combination of TE and TM mode is called transverse electromagnetic mode. Here the total field lies in the transverse plane, that is perpendicular plane. That should be both EZ and HZ are 0. Okay, then we are going for exact definition of mode theory for circular waveguide. So to understand the power propagation in an optical fiber, we need to solve the Maxwell's equation with the condition of cylindrical structure. Why? Because our optical fiber in the form of cylindrical structure. So when solving the Maxwell's equation for hollow metallic waveguide, only the TE or TM modes are found. But in optical fiber, because of the core cladding boundary condition that leads to coupling between the electric and the magnetic field component, then this is called hybrid mode. Already we have seen this. Okay, now we are going for the Maxwell's equation. So remember, in the time varying nature of the Maxwell's equation, we have four different equations. One is Faraday's law. First equation based on the Faraday's law, and the second equation based on the Maxwell's Faraday equation, we are getting magnetic field intensity H. And the third one, electric Gauss law, del dot D equal to 0, and fourth one, Gauss law for the magnetization. So first two equations, del cross E and del cross H, where we are going to find out the curl of a given vector. So curl of electric field and curl of magnetic field. And when you go for 3 and 4, where we are using divergence, del dot D and del dot B equal to 0. Okay, so here we are going for the important parameter with respect to medium. So B we can replace by mu into H. So B, it is a magnetic field intensity, and H it is a magnetic flux density and intensity. So D, it is electric field intensity and the electric flux density, and E is equal to electric field intensity. So D is directly proportional to E, and we are going to replace the direct proportional by a constant is called epsilon. So epsilon, it is a permittivity of the medium, and when you talk about magnetic field, where mu is equal to permeability of the medium. Okay, so consider the first equation, then we can multiply del in both sides. So del cross E is equal to minus mu dou by dou t of del cross H, that is equal to minus epsilon mu dou square E by dou t square. Okay, so using vector identity, the del cross E. So here look at that, in a single term we have two multiplication with the del operator, so that this will be represented in terms of identical form. So del cross E is equal to del of del dot E minus del square E. So vector identity. And when you talk about the del dot E in a free space, del dot E equal to 0. So in the equation 6, the first term, that is del of del dot E is equal to 0. So we have only minus del square E. So we can substitute this one into there. We'll get del square E equal to epsilon mu dou square E by dou t square. So this is in the form of electric field intensity. So similarly, we can find out the magnetic field intensity. Then it is like del square H equal to epsilon mu dou square H by dou t square. So the finally equation 7 and 8 represent the standard wave equation, right? So in terms of electric and magnetic field with the time varying in nature, 7 and 8. So these equation known as standard wave equations. So modes are can be solving by using the equation subject to the core cladding boundary conditions. So thank you all. Thank you for watching this video. Thank you.